Okay, 9.7 part 2. Sorry about the interruptions on the first one. So again,
What number again?
I just did this one. Okay, so to recoup here, what we're trying to do is fill out this table. For each city, they've either given us a table, a graph, or some words to talk about how the population is changing either in the last couple of years, right now, or in the upcoming years. So what we need to do for each one is find out if it's a constant rate or a non-constant rate. If it's a constant rate, we need to find the actual rate. If it's non-constant, we go skip this one and go straight to what kind of function is it. So our options are quadratic, exponential, or inverse variation. And then we have to predict, okay? So as you listen to me, you'll be able to stop and pause the video and fill in what you need to in this table. Okay, so again, 3 things that we need to find for each city. Is it a constant or non-constant rate of change for the population? What is the rate or the relationship? And then predict the future. So we're on the second one. We've taken care of Big Rock. Let's talk about Triple Falls. All right, so Triple Falls, when you take a look at it, we've got population on the Y, and we've got elapsed time in years over here on the X. So I automatically know that it's a constant rate of change because it's a line. If it's a straight line, I don't care if it's pointed up, down, or straight to the side, if your dots form a perfect straight line, then you are, in fact, constant rate, meaning you're growing at the constant speed. I don't like to find, it's hard for me to find a rate from a table, from a graph. So the next thing we need to do is actually find the constant rate. So I like to actually take these and put it in a table. So here's what I did. 1 year, 6,000 people. 1 year, 6,000 people. Second year, 6,100. Second year, 6,100. 3 years, 6,200. 4 years, 6,300. So all I did was make a quick table out of the dots that they gave us. 1, 6,000, 2, 6,100, 3, 6,200. I know that population's my Y, so I put that over here on the right-hand side. And I know that years is my X, so I put that on the left. So now we have to test. Is it a constant rate of change? Well, the first rate of change is 100 divided by 1, which is 100. The second rate of change is 100 divided by 1, which is also 100. The third rate is 100 divided by 1, which is also 100. So my rate of change every single time was positive 100 population per year. It might make a little bit more sense if we just say people per year. So every year, you're adding 100 people. So our rate is 100 people per year. All right? So let's review what we did here. We found the common difference, which is finding the first difference of the Y and the first difference of the X. They're all the same, so that means it's a common difference. They're common difference, that makes sense. Common difference equals linear. Linear equals constant rate of change. So we know it's a constant rate of change for Triple Falls. So if you want to pause it now and fill that in on your table, you should. This is how I actually found the true rate. How is this city growing, or how is it decreasing? Well, you take the change in Y divided by the change in X. So change in Y divided by the change in X. The change in Y is always 100. The change in X is always 1. So we have 100 blank per blank. A rate always has a unit after it, and it's something per something. Remember, it's Y per X. Y is the number of people. X is the number of years. So my rate of change is a positive 100 people per year. Again, we're filling in that table slowly and surely. Okay, next one is Waltersville. So let's take a look at Waltersville. First, let's decide if it's constant or non-constant rate of change. A constant rate of change, this divided by this, so 1506 divided by 1 has to equal 2510 divided by 1, and has to equal 3514 divided by 1. What I'm doing is finding the individual speeds of between each dot. Obviously, 1506 divided by 1 does not equal 2510 divided by 1 does not equal. So if they don't equal each other, it can't be linear, which means it can't be constant. So we know it's non-constant. So take a minute now, look at your table, and for Waltersville, make sure you write down non-constant for Waltersville. All right, so first difference didn't work out for me. So let's try the second difference. If I find the difference again of these guys, take a look at what I get. I get 1004, 1004. If the second difference is the same, it's quadratic. So let me explain how you're supposed to be filling in this table. So Waltersville, we've decided, was non-constant. So I found Waltersville, constant or non-constant. It's non-constant. Its speed is changing. If it's non-constant, we skip this one. And what kind of function is it? Well, it's quadratic because of the second difference. So I'd write quadratic here, and then you guys can go ahead and make your own prediction. All right, let's get back to it. So we found that this is quadratic. All right, so let's take a look at the next one. The next one says we're talking about Rapid City. So on your table, find Rapid City, that's what we're talking about. It says that there's been a steady loss of 4,000 people a year. Well, steady is a synonym for constant. So steady and constant go together. So find Rapid City, and we know that that's constant. Now, if it's constant, we have to find that actual rate. Well, to find that, we could make a table. If we made a table, it looks something like that. Right now, it says that there's 15,000 people in the city. It also says that we're losing 400 people per year. So after 1 year, I'd be 400 people less, which is 14,600. After that, I'd be 400 less than that. After that, I'd be 400 less than that. So my rate is something blank per blank. So it's negative 400 people because we're losing 400 people per year. This city is actually getting smaller. So the rate is decreasing. You're losing negative 400 people per year. So if I were to pause here as a student, I would come back here and it says, what is the rate? Well, the rate at Rapid City is negative 400 people per year. All right, now that I've shown you how to fill out this table as we move along, you can pause it on your own to fill this out. All right, next city is called Bristol. If I connect all those lines, it is not a straight line, which means non-constant rate. It is a non-constant rate. Okay, so let's take a look at this graph. When they give us a graph, it's non-constant, so we've got to decide, is it quadratic? Well, if you remember a quadratic, look what letter's there. It looks like a U. Does that look like a U? Nope. Our next was exponential. Exponentials come down and go like that. That doesn't look like that, so it's not exponential. Inverse variation, remember, stays in its own little corner of the graph and never touches it. So it doesn't look like any of those. So this would be a none. So you'd come over to Bristol. We decided that it was non-constant, so we don't have to find the rate. And what type of function is it? It's a none. You can go ahead and predict how much in the year. All right, moving right along. Next one we've got Rock Canyon City. Rock Canyon City, it looks like the weather lady? I don't know, somebody here. It looks like a news channel. Every year, about 500 new people move into the town. Well, that's easy. Every year means it always happens at 500 per year. So it's steady, which is another word for constant. So this one is going to be constant, which means it is linear. Yes, Vivian helped me with that one. Shout out to Vivian. Now, let me show you something about Rock Canyon City. Rock Canyon City said that 5,000 people were there 4 years ago. So if there were 5,000 people 4 years ago, when we make a table, we need to make sure that...
Cake.
Oh, yay. I just got cake.
Did you want a cup of fruit?
No, I'll take the cake over fruit.
Okay.
Being super healthy today. Thank you, Miss Laura. Okay, sorry. No. Okay, so in here it says that there were 5,000 people in the city 4 years ago. Well, we've already discussed so many times in class that right this second is 0. 0 years from now is right now. 1 year ago, 2 years ago, 3 years ago, 4 years ago, there were 5,000 people. It also said that 500 people moved every year. So 4 years ago, there were 5,000. Then 3 years ago, there has to be 5,500 because we added 500. 2 years ago, we're getting closer to the present, 600. 1 year ago, 6,500. So right now, there's 7,000 people. So your prediction should be spot on. In 1 year, there should be 7,500 people. We know that we have a constant rate. Constant rate means linear. It's going to make a straight line. If we wanted to find the rate of change, which we have to, it'd be the change in y divided by change in x. The change in y every time is 500. The change in x is 1. 500 divided by 1, people per year. 500 people per year. All right, that's Rock Canyon City. We've got one more, right? Yep. What's this town called? Hettsburg. So let's talk about Hettsburg for a second. I said that since I told you guys how to, sorry, there's an audience here. I told you guys how to fill out the table, that you can fill it out on your own.
Hi.
All right, so we're talking about Hettsburg. Hettsburg is bursting at the seams. So instantly, when they say bursting at the seams, do you think growing at a small rate or growing at a very big rate? You should think growing at a very big rate. The population is doubling every year for the past 3 years. 4,000 residents live here right now. So let's talk about a table. If we had to make a table for Hettsburg, they told us right now, year 0, that's right now there's 4,000 people. It told us over the last 3 years, so in the past for 3 years, it's doubled every time. So 1 year ago, it had to be 2,000 if it doubled to get to 4. This number had to double to get to 2, so it's got to be 1,000. This number had to double to get to 1,000, so it had to be 500. So take a look. Right now, there's 4,000 people. 1 year ago, it was 2,000, and then it doubled. 2 years ago, it was 1,000, and then it doubled the next year. So what do you think that next year, if 4,000 is right now, 1 year from now, how many people do you think are going to be there? Anybody? Bueller? 8,000, because it's got to double. So I need to know, is this constant? So let's take a look. I found the first difference on each side. Is 500 divided by 1 the same as 1,000 divided by 1? The same as 2,000 divided by 1? No. Look, this year it's at a speed of 500. This year it's a speed of 1,000. This year it's a speed of 2,000. So the speed is changing. When the speed is changing, that means it's non-constant. It's a non-constant rate. So now that it's a non-constant, we have to decide again, is it quadratic? Is it exponential? Or is it inverse variation? Well, quadratic says the second difference must be the same. So if we find the first difference, this went up by 4,000. This went up by 2,000. Is the second difference the same? Nope, so it's not quadratic. Let's talk about inverse variation. Inverse variation is where the x goes up and the y goes down. The x is getting bigger, so the x is getting bigger. The y is also getting bigger. So it can't be inverse variation because they're moving in the same direction. X is getting bigger and y is getting bigger. Inverse variation means opposite. So exponential, remember that the test for exponential means you had to have a common multiplier. If I can multiply by the same number all the way down the stack of y's, then I've got exponential. Well, I can multiply each one of these by 2 to get to the next one. 500 times 2, 1,000. 1,000 times 2, 2,000. 2,000 times 2, 2,000. So it is, in fact, exponential. All right, use what we've done here to go ahead and help you fill out the rest of these. When it says pick two cities and represent the data in two different forms, all you have to do is show me this work. Look what we did. We took a graph and we made it into a table. That's changing it. We took words and made it, oops, where's Rock City? Rock Canyon. The heck is Rock Canyon? Rock Canyon City, we took words or a verbal description, we made it a table. So we're showing it in two different ways. So if you show me this work, then you don't have to do anything for this one. All right, and then the last one, I wanted to give you a quick snapshot of what I think for staying sharp. So I'm going to leave this here. You can pause it. And try to make out my work. Me. You can pause it wherever you'd like. And there's my hint for the second one. All right, see you in class.